We're going to start discussing now the greenhouse effect. And to start, we're going to start thinking about objects and the materials in the Earth that actually have a specific temperature, and this is linked to the peak wavelength of radiation. So Wind's displacement rule gives the wavelength at which a blackbody spectrum peaks as a function of its absolute temperature. So this equation is going to help us to know when objects have the radiation, the maximum of radiation, right? At which wavelength? In Wind's equation, we have the lambda with the max, which is in micrometers, and then which is the wavelength, and then we have temperature in Kelvin, and the 2898 is called the Wind's constant. And then with this relationship, we can have, you see that if the temperature of a body is high, the radiation, the wavelength of radiation will be short, and will be the opposite if the temperature of the body is at low temperatures, right? So the sun can be represented as a black body with a temperature of 5800 Kelvin. And the spectrum peaks at 0.5 micrometers. And let's keep in mind this value because we're going to start having a comparison among different objects and also a comparison with the Earth. The Earth at 288 Kelvin has its peak at 10.1 micrometers. So this means that the sun has a peak in the short on the short wavelength, and the Earth has the radiation, outgoing radiation, at long wave length, right? The area under this course between any two wavelengths is the total radiant energy in the range of frequencies. So, for example, the area under the curve of incoming solar radiation just outside the atmosphere is the total solar radiant flux, which is 1,370 watts per square meter that we discussed in our last session. So notice nearly all the incoming solar energy as it arrives just outside the Earth's atmosphere has wavelengths less than 3 micrometers, while the outgoing energy radiated by the Earth has essentially all of its energy on wavelengths greater than 3 micrometers. So with so little overlap, it is convenient to speak of solar energy as being short wavelength radiation and Earth's surface as long wavelength radiation or thermal radiation, right? So the infrared portion of the spectrum begins at about 0.7 micrometers and extends out to 100 micrometers. So some of the incoming solar radiation and all of the outgoing thermal radiation is infrared, all right? So as radiant energy attempts to pass through the atmosphere, it is affected by various gases. And these gases also have specific peak wavelengths of radiation. So those atmospheric constituents can let radiant energy pass through unaffected, or they can scatter the energy by reflection, or they can store by absorption. So the key phenomenon of interest here is the ability of gases to absorb radiant energy. As the atoms in gaseous molecules vibrate toward and away from each other, or rotate around each other, they absorb or radiate energy in specific wavelengths. So this is a figure where I'm showing you different gases, different compounds that have specific wavelength peaks within the overall spectrum, right? So when the frequency of these molecular oscillations is close to the frequency of the passing radiant energy, the molecule can absorb that energy. This absorption occurs over a rather limited range of frequencies, not just at the oscillatory frequency of the molecule, and results in an absorptivity spectrum, which is a plot of the fraction of incoming radiant energy that is absorbed as a function of wavelength. So in the figure on the left side, you can what we are presenting is key greenhouse gases that are concerned and that they have a key way of absorbing energy. So most of the long wavelength energy radiated by the Earth is absorbed by a combination of these active gases. So most importantly is the water vapor, the carbon dioxide, the methane, the nitrous oxide, and the ozone. Water vapor is by far the most important greenhouse gas. It strongly absorbs thermal radiation with wavelengths less than 8 micrometers and greater than 18 micrometers. And carbon dioxide, as you can see, has also a strong absorption band, centered at 15 micrometers, and then also as well as in band centered at 2.7 micrometers and 4.3 micrometers. And then we have a kind of a window. It's called atmospheric radiative window, which is between 7 micrometers and 13 micrometers, where there is not a clear sky for outgoing thermal radiation, right? There is a window where there are no gases that will absorb this energy. So radiation in those wavelengths easily passes through the atmosphere, except for a small but important absorption band between 9.5 micrometers and 10.6 micrometers, which is associated with ozone. So radioactive gases that absorb wavelengths longer than 4 micrometers are called greenhouse gases. This absorption hits the atmosphere, which in turn radiates energy back to the Earth as well as out to the space. These greenhouse gases act as thermal blanket around the globe, and which allows raising the temperature, right? So why do we compare the greenhouse gases with the greenhouse that is constructed made of glass? So glass, which is easily transmits shortwave solar energy into the greenhouse, absorb almost all of the longer wavelengths radiated by the greenhouse interior. This radiation trapping is partly responsible for the elevated temperatures inside the greenhouse. So opposite to this, the greenhouse gases actually do not reflect the infrared. They instead absorb and radiate it. And that's the difference between both. So now we're going to add to our zero balance model the role of the greenhouse effect to the balance. So let's go back to remember that if the Earth did not already have a greenhouse gas effect, its temperature will be minus 19 degrees, right? Or 254 Kelvin. So to quantify the magnitude of the greenhouse gases effect, we can compare the effective temperature that we get before with the actual temperature in the surface, which is called Ts. So since the actual temperature of the Earth is 288 K and its effective temperature is 254 Kelvin, we can say that the greenhouse gas effect adds 34 degrees of warming to the surface of the Earth. Okay? So based on this, we can actually have a comparison of the actual surface temperatures with the effective temperatures. And here we have a table where we compare actually temperatures of the Venus, Earth, and Mars. So they have different characteristics. They have different atmospheres, distance from the sun, and they also have different albedo. So you can see, for example, that the surface temperature in Venus is very high, is 750 Kelvin, right? And this is connected, of course, to the amount of CO2 that the planet has, all right? In Mars, in contrast, we have a very low surface temperature, which is 218 Kelvin, and this is connected to the lack of atmosphere, as you can see on the table. Even though there is CO2 in Mars, there is a presence of this gas, but it cannot really act as a greenhouse gas because of the lack of atmosphere. So then we can, from the comparison of TS minus TE, we can have also the definition of greenhouse gas warming. So it's a difference, and we can see how important is the greenhouse gas effect on these planets. So the impact of greenhouse gas emissions upon the atmosphere is also related to other properties, not only the radiative ones, but also to the time scale that characterize how much time it stays or it stays in the atmosphere. So radiative properties control the absorption of radiation per kilogram of gas present at any instant. But the lifetime controls how long an emitted kilogram is retained in the atmosphere, and hence is able to influence the temperature, right? So we've been discussing a lot about carbon dioxide as the main gas, but there are some other gases that also have an effect, a greenhouse gas effect, right? And these were discussed also in terms of the wavelength, right? The peak of the wavelength that they at which they absorb. So so then we have a way of assessing. We have two ways of assessing the effect of these greenhouse gases. One is the lifetime in years, and the other aspect to look at is the global warming potential. So global warming potentials are a measure of the relative radiative effect of a given substance compared to another, and integrated over a chosen time horizon. The choice of this time horizon depends in part upon whether the user wishes to emphasize shorter term processes or longer term phenomena. As short-term processes, we have responses of cloud cover to surface temperature changes, and for example, long-term phenomena can be the sea level rise that are linked to sustained alterations of the thermal budget. And we, talking about this, we need to mention that, for instance, the role of how the carbon dioxide goes to the atmosphere is also connected, and later on we will see these feedbacks, because, for instance, carbon dioxide also, if it rises, it can also rise. It has a lead to the increase in temperature, right? Temperature in the earth. But if we increase the temperature in the earth, there might be some other effects that will increase the carbon dioxide in the atmosphere. For example, one of these is the equilibrium on the oceans, of the CO2 in the oceans. That is ruled by the chemical equilibrium of this compound, and the other is also due to the temperature. But also it can also lead to other effects that are secondary effects of climate change. So in this table, what I'm showing you is the lifetime in years, and you may see, if you Google this lifetime in years, you may see that this can vary among authors or literature, okay? There is some small range because the scientists have calculated this in different ways. And we have the main greenhouse gases. Well, here we have carbon dioxide, methane, and nitrous oxide. But there are other gases that can also remain in the atmosphere and that can have an effect, right? So we have also the reference gas will always be the carbon dioxide, and that's why everything is called, when we have talk about greenhouse warming potential, or in terms of comparison with other gases, we will talk about equivalent CO2 equivalent, right? So the reference will be 1, and then we will have methane. Actually, to look, if you see it, it has a greenhouse gas effect that is way much higher than carbon dioxide, right? So that's why we are looking at different processes on Earth that actually emits methane. because it is very important. And then we also have nitrous oxide. It is interesting to see that carbon dioxide, the lifetime in years, is not defined. And this is because it really depends about what we were talking about, short-term and long-term phenomena. Okay, so for instance, the renewal of all the human emitted CO2 from the atmosphere by natural processes will take a few 100,000 years. And so, but there are some other carbon budgets that can remain in the atmosphere in a shorter period. Okay.